data acquisition system and signal processing solution for custom designed microscope. But talking with some of you, and there's Q&A time throughout the session. So I would like to ask if any one of you knows what is this site for? Do you know where you are? Yes. Okay, some of you, yeah. Okay, good. So essentially, when I applied for the conference, it just said Sydney. And I was surprised because my office is just down the corridor. So it's National Measurement Institute and CSIRO, but I think it could be easily from 2027 because CSIRO is moving to Bradfield City. It's just going to be National Measurement Institute. Okay, so I have this generic slide for when I usually give a talks outside Sydney, but our main office is actually here, although we have offices throughout Australia. We have roughly 400 staff, 800 million in budget. So we are part of the federal government, and what we are is really the Australian peak body measurement for physical, biological, chemical, legal, and trade measurement. So many people talk about quality, so I'll just add here that good practice, if you want to start in the right way for any of you manufacturing, is start with metrology, because that's the beginning of the things. As we will see here, if you want to do the for example, dimensional measurement, you have to kind of connect to SI definition of a meter, which is defined through the frequency of laser light. And that's what gives you what is known as traceability. And then with an NMI, we are doing a lot is we want to boost the accuracy. And in our case, for dimensional measurement at the nanoscale, we are targeting something like 1 nanometer uncertainty in this volume, 100 by 100 by 25 micron. Okay, so where our instruments sit is if you have SI definition of a meter, realization of the meter, then you have to calibrate the laser frequency, and then it's our instrument known as primary standard for nanometrology. I would like at this point to emphasize, so this instrument is designed and built in Australia. Some components are commercial, but it's actually something which you cannot buy commercially. Okay, so this is the instrument. As I already mentioned, through laser interferometry, we get traceability, but there's lots of mechano-optical, electrical parts which go in it, and that it's real. I'll just show you here. It's essentially atomic force microscope with a well-controlled environment and interferometry. So our challenge was really, and we were fortunate enough to have this project going, to figure out how we're going to do the data acquisition, also at the same time monitoring all the signals. So that was the really problematic, because just if you want to being able to evaluate your accuracy or your uncertainty budget, you really have to take care about, for example, measuring temperature gradient, pressure, humidity, CO2, which all comes to, for example, refractive index of light. And for that reason, we also try to obviously reduce those uncertainty components by putting all our heat sources in one room and just getting the instrument in the other room and having optical fibers in between. That's just an example. Okay, so as I said, it's challenging how you now, integrate all these things together and get it going. And we thought because of different reasons, but primarily that something is scalable and modular, we found this PXI solution, which offered us opportunity by putting different kind of cards that we could do all what we need to do. I'll just come back again to, for example, of interferometry, because that's the really critical component in our instrument, that we use heterodyne interferometry. So what you only have to remember is there are two frequencies of light going between the reference and movable mirror. But obviously you can measure the signals, but that doesn't tell you the displacement. So you have to build digital phase meter, which tells you from the phase difference between these two signals, what is the displacement. And in our case, we use a commercial interferometer, which is double pass interferometer. And this is the generic formula how you get from the phase, you can get the displacement. And then once you want to implement that, you want that it has sufficiently high bandwidth. You want to have stable things. So we decided to do on FPGA and using NI solutions. So for that, you would need two phase locked loop. Then you need digital integrators, and as shown as this schematics. Then you need some filtering. And then at the end, you need to subtract the reference phase from your signal phase. And that also immensely improves by reducing common mode noise sources, signal to noise ratio. So just how you implement that in LabVIEW, I'll just give you a simple example, because anyone can do this really in LabVIEW, and that's the advantage. You don't have to be professional FPGA encoder. So you mix, you just multiply, then you integrate your signal. Then for NCO, this is how it looks like. And then filtering, and it's democratized almost what people can do LabVIEW, and that's why LabVIEW is great. So this is the performance of our phase meter, and you see that we get deep sub-nanometer placement measurement. So I'll just mention that there's another issue. So what I told you, this is Microscope, and you have a bunch of other signals coming from Microscope. So you have to kind of sync them, and the way we do it is through the TTL signal between the controllers. So we can do the data acquisition, capturing all these signal channels which are related, let's say, to environmental control, and then we do this point cloud. We can then plot whatever we would like and visualize later on. So we don't do that in real time yet. And that's maybe something which LabVIEW is not good at. I have to have some critical thing here about LabVIEW. And obviously you could have another option is to even have timestamp and then to kind of do everything offline, but that's harder. So having TTL signal, putting in PXI, appropriate card gives you this counter and triggering event. And then you have to kind of get from the RT to your computer. You have to transfer the data. You may have some issues, but eventually you will make it work. This is how it looks like. This is that room which contains all the controller. This is the friendly interface for our phase meter. And then besides this, I mean, we have different things for our alignment of interferometers. Here you can see where we have this sort of 4-quadrant detectors with our signals. And this is 4 of them. And then we have TTL signal, which was just here for testing purposes, all this interface. So I'll stop there, and if you have any questions, I'm happy to answer. Thank you for your attention.